Welcome back to our discussion of AP Chemistry equilibria with acids and bases. We were introduced last time to the idea of Ka, the equilibrium constant with an acid. Again, the little subscript A really is not important. It is still worked like an equilibrium reaction. I do point out that we only have really use of Kas for weak acids, and the same would be true of weak bases. And when we do our equilibrium constant expressions, I remind you we still do not include pure liquids like water or pure solids like we did with KSP. So do be watching out for that. That's a constant thing that is going to be true about what we're doing. Okay, so we're going to look at what is the equilibrium concentrations of this thing, okay, which is actually hypohydrous acid. If 0.1 molar solution of it has an equilibrium constant of that. So of course we probably want to focus by writing our our balanced chemical equation. And because water is not included into our equilibrium expression, I'm really not going to include it in with my reaction as well. You could, certainly, but I don't feel it's necessary, and it does help to simplify things. I guess changing the brightness doesn't really make it show up any easier. So I didn't even need to know the identity of this acid to predict that that H in front would ionize, and there we go. So that's my R. That is my reaction. Now I'm looking for my initial. Initially, if I'm reading the problem, initially I have a molar solution of that and none of the ions. And so I want to know how much will ionize. Well, that is how much will be lost here and how much will be gained here. And the answer to that is I don't know. But I do know it's a 1:1:1 ratio. Always check your ratios because there are acids that are diprotic and triprotic. Same with bases. You can have bases with 2 hydroxides, 3 hydroxides, stuff like that. So watch out, be careful. So what do I know at equilibrium? At equilibrium, I know I have 0.10 molarity minus X and X and X. And I would write my equilibrium constant expression because I want to get that point in case it's a point. Nice, easy point. Concentration of hydrogen ion, first order. Concentration of chloride ion, first power there. There is a negative there. Be sure you include ion charges or you're writing it wrong. And now I'm going to substitute in. And when I substitute in, I get x squared over 0.10 molarity minus x. So I can already tell, and I'm going to substitute in the number I was given, 3.5 times 10 to the negative 8. I was given the Ka. And so I can already tell I'm going to use the quadratic equation. Or am I? Do you remember our discussion in all of our equilibrium ones actually about simplifying and avoiding that quadratic equation? My question to you is, would it work? Is this a small enough K that I can assume that this X here can be ignored? Not these X's. If you ignore all the X's, you'd have like 0 on top, and that's not right. Can I, with this small a K value, ignore that? Well, remember, K tells us how much this will react. This is going to react a really, 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 really small amount. This is a decimal point and 7 zeros before you hit the 3 and the 5. So yes, this part here, that X, is ignorable. So what that really means, and I would make a statement about that because Ka is much, much less than 0.10 molarity. Assume 0.10 molarity minus X is equal to 0.10 molarity. Make an assumption. Show that that's what you're doing, because especially on the AP test, they want to see that you've done that because that proves you know some chemistry. So now I have X squared over 0.10 molarity equals 3.5 times 10 to the negative 8. And so x equals, and here's where I'm glad. Here's where I'm glad that I have a calculator. But if I did not have a calculator, if this was mental math, that would multiply, and that's 10 to the minus 9. And then a square root is taking the exponent to a half. These are things you were taught in math class, and you were taught them for a reason. I just wish they would have shown you the actual reasons, and not just because this is the way it goes. The reasons is we actually like to use them then for estimations in chemistry. So anyway, I'm going to take my k value and multiply by 0.1, and I want to be sure I square root that. And as I'm having issue finding a square root button on my calculator, what's the other option? The other option is to raise it to the power of 0.5, which is 1/2, which is the same as the square root. So again, nice little tricks if you know math, philosophy, that can help you out. I get, and I'm going to write it in scientific notation because that just is kind of the way we tend to do it. It doesn't matter. I have officially said that, so please listen. It does not matter if you use decimal or scientific notation as long as the number is the same. And that's 1, 2, 3, 4, 5 moves of the decimal. So 5.9 times 10 to the minus 5. Now wait, I've been looking for concentration. Molarity is my label. I have to stick that on there because we have to undo that whole fugacity thing that was done to get a label-less K value. So now I have what X is. What would answer the question? What are the equilibrium concentrations? So I want the equilibrium concentrations of everything. Well, this concentration equals the concentration of H plus and equals the concentration of OCO minus, which is probably what we in pre-AP wrote as ClO minus, the same thing. And so let me ask this. Now that I actually know what X is, should I bother putting X in there and subtracting to answer, or do I leave it off because we made the assumption? And the answer is it doesn't really matter. Because either, prove it to yourself, take 0.1 and subtract that, and then round to 2 significant digits. And you're right back literally where you started from. Well, it's supposed to be 0.10. Molarity is the concentration of HOCl. So it is such, wow, that's a CO. It is such a weak acid that we have almost entirely the amount of, original amount left over after the ionization. The ionization is so small, it's almost not even worth looking at. Okay, let's try a different one. Calculate the percent ionization of a 0.1 molar acetic acid solution. Okay, well, for percent ionization, I probably want to focus with a balanced chemical equation. So here's acetic acid, okay, and it's going to ionize. And for percent ionization, I'm going to need to know a final molarity, so I can subtract from my initial molarity, divide by my initial molarity, and then multiply by 100 to find a percentage. Fun stuff like that. So I have a balanced equation that's going to focus me. My initial amount, 0.10 molarity, 0 and 0. How much will I lose? That's an I don't know in wine, which I get from you as students all the time, which is really annoying. And then at equilibrium, 0.10 molarity minus X, X, and X. Oh wow, it's looking very similar to our previous question, only it was different things. But that's fine, because that's why I'm doing it. It's very similar in form. It's a different reaction, and I'm looking for percent ionization for my final answer, but we'll get to that. So what do? I write my Ka expression. So I'm going to have concentration of H plus, concentration of C2H3O2 minus, and I'm going to divide that by concentration of HC2H3O2. Okay? And I'm ready to plug in numbers and solve for X, and you're like, wait a minute, I need a Ka if I'm going to proceed, and you're absolutely right, and I did not give you a Ka. Well, I did not give you a Ka in this value. Okay, so check this out. right here. Okay, we found a Ka for acetic acid. Okay, so it's something we already did in our notes. And here's the best part. The back of the book and even Wikipedia, or even honestly just straight out Google, if you were to Google what is the Ka of acetic acid, I'm sure you'd get the right answer. It's very, Kas are a very common thing in chemistry. You're going to get lots of hits on, charts of Ka values. So you look it up is what I'm trying to get at. So if you don't know a Ka, you're supposed to look it up. Now on the AP test, of course, you can't look something up during the middle of the test, so they would give it to you. And if they did not give it to you, there's a way to figure out your answer without it. But here in the notes, I expected you to look it up or look at our previous example. Ka for acetic acid is 1.8 times 10 to the minus 5, if I remember correctly. So even if I don't remember correctly, just pretend I am correct, because of course I'm always right. So there's our Ka, and check out what I notice. That would make that x ignorable, very, very small. So I can do the assumption, and I would write the words, assume, blah, 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 blah. We've done that many times before. You can handle that by now. If not, come in after school, I'll pull out my 9-iron and I'll teach you a lesson. And that is a joke. So if you really do want to understand when can I ignore that or not and where, please do come in and get help on that. That's important. So what I have, actually I don't want my equal sign there, sorry. What I have is an x times an x divided by a 0.10 molarity equals 1.8 times 10 to the minus 5. And again, I'm going to solve for x. And x is going to be helpful because it is the concentration of H, and it's the concentration, there's an equal sign between there, sorry, concentration of acetate ion. Okay, so now again, oh so much fun with the calculator time. So 1.8 times 10 to the minus 5 times 0.1, and then I'm going to square root that or raise it to the 1/2 power. Either way works. Okay, and I hope you're following along on your calculator too. Actually, I'd rather have the equal sign over here. Equals, oh my goodness, this is fun. 1.3 times 10 to the 3. Negative 3. And it's a concentration, so I want molarity. Okay, so there's my answer to, oh wait, no, there's not my answer. I wanted percent ionization, and that is a concentration. Well, I'm on my way. Percent ionization would be how much ionizes, how much do I lose of the original amount. That's how much I lose. My original amount is a 0.1 molarity. And I am going to show the times 100 because on the AP test they have said they want to see the times 100 when you do a percentage. I don't know why they are picky about that, but they are. So I'm just passing that along to you. Okay. So 1.3%, no. Wow, did I just kill that? Good job. Good thing that I have a calculator with a large screen to notice that I did not type that in correctly. It helps if you divide by the correct thing before you multiply by 100. Okay. So that divided by that times 100 is 1.3, flat out 1.3%. Okay, rounding the 4 down, it says the 3 stays the same. There we go. So 1.3%. So very low amount for that. Okay, so very, very low amount on our acetic acid, but that's what I expect. Acetic acid is a weak acid. I expect a low amount of ionization. And in fact, acetic acid is vinegar. And since we use vinegar in food, I really do hope it's a small amount of ionization, because I would certainly not want to use a strong acid in food. That would be really bad. Okay, so there's 2 examples of how we can take Ka to find equilibrium concentrations, whereas last time we took equilibrium concentrations and found Ka. Things I want to remind you of that that you should have caught by now, and if you haven't, then I'm flat out telling you. Okay, again, and I said this last time, and I'm saying it again this time, the higher the Ka value, that is the smaller the negative exponent is, then the stronger the acid is, and the closer the pKa value will be close to 0. Be sure you can connect those in your head. There's most definitely a connection between the size of the negative exponent, the value of pKa, and the strength of the acid or base. Definitely a connection. Be sure it's connected correctly in your head. Okay, and the thing students most often miss, I'm just warning you, they'll see 10 to the negative 5, and then they'll want to compare it to like 10 to the negative 7 and say 10 to the negative 7 is bigger. Well, no, that negative sign means it's actually a smaller number. So please, please be careful. 10 to the negative 5 is bigger than 10 to the negative 7. So please be careful about that. Please, 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 please be careful about that. Because guess what? Students like to mess up all the time. So be careful about that. And as we said in the other times that we have made our assumption, that it helps if you have a 10 to the negative 4 or larger difference between your quantity you want to ignore x from and your Ka. Now, if this number, because here my Ka was 1.8 times 10 to the minus 5, if this number was like 1.0 times 10 to the negative 4, the difference between them is not large enough. This is definitely large enough. If I got even a 0.001 molar, that'd be 10 to the negative 3, I really wouldn't want to make the assumption there. And I'd want to see what the quadratic shows me. So, rule of thumb that I just tend to go off of is I check, is it a 10 to the minus 4 difference? If it is, then you're safe. Honestly, a 10 to the minus 3 difference, you're probably still safe. A 10 to the minus 2 difference, don't do that. Please do not do an assumption when it's that close, because now you could be off by a tenth, not just a hundredth or a thousandth. I prefer a thousandth, okay, but it could be off a lot. So be very, very careful that you compare it to the concentration of your acid. And if that is 10 to the negative, if Ka is 10 to the negative 4 smaller, then it's definitely safe to make the assumption. And quite honestly, with our acids and bases, it will be, because again, the only acids we'll use Ka and Kb for really is weak acids and weak bases. And by definition, weak acids and weak bases don't ionize well. So I hope I've harped on this enough. I know you're like, think I'm redundant, but this is a constant, these two are constant sources of confusion for students, and I don't want you to get trapped like past students have. So please be careful about that. We're actually going to stop here for now because I want you to do some practice with using Kas to find some equilibrium concentrations. So good luck on your practice.